Good day. I want to talk today, this is lecture 21, about section 8.2, which concerns surface area, the surface area of a so-called surface of revolution. Okay, here's the setup. You have a curve. Maybe it's, and it's defined between A and B. And what you do is you spin it or rotate it around the x-axis. You could also rotate it around the y-axis, but let's talk about the x-axis first. This will generate a solid, or a surface, I should say, a surface of revolution. It looks something like this. So there's a surface of revolution. Okay, so now the way we calculate this, the surface area of a surface of revolution, is we take a little section of it, which is determined by having a little subinterval in a subdivision. So here's a strip, and if we look and we blow this picture up, so I'm going to blow it up, you get a picture that looks something like this. It looks like a ring or an annulus, and the length of this piece is of the form delta S, where delta S is the length of the curve. Okay, now if we want to calculate the area of this little piece of surface, we need to know how to do that. Well, it's given as follows. We can take the area of this is approximately equal to the circumference, the circumference of the circle that's in the picture times the length, delta S. So if we call the radius capital R, this is 2 pi R times delta S. Now, what is R? R is the height of the curve. So that would be f of x or y. Okay, so therefore, this is the same thing as something like 2 pi y ds if delta S is small. And now we're going to be summing up over all such little pieces of surface to get the actual surface area, and we're taking a limit as delta S gets small. And so this suggests the answer that the surface area is given by the integral from A to B of 2 pi y ds. And what is ds? ds is equal to the square root of 1 plus dy dx squared times dx, if we like, or if you want to use the dy, it's also, we saw last time, 1 plus dx dy squared times dy, depending upon whether you have the function y is in the form f of x or x is in the form f of y. And this is around the x-axis. Okay, so that is the general statement of what the surface area is. And now I'm going to do some problems. So I need to clear the screen. Okay, so let me start with example, a sphere of radius A. So how can we get a sphere of radius A? Well, we can take the upper semicircle, y equals the square root of a squared minus x squared. Here, a is a constant, obviously. And we can rotate it around the x-axis to get a sphere. So now it's also, it's actually convenient to just use a quarter circle and then multiply the result by 2. So let's use the quarter circle. It makes the integration a little easier. Okay, so what are we doing? So y is the square root of a squared minus x squared. So dy dx is 1/2 a squared minus x squared to the minus 1/2 power times negative 2x. That's the derivative of the inside, which gives me minus x a squared minus x squared to the minus 1/2. Okay, so that's dy dx. And so what do we get? So the surface area is going to be the integral from the two endpoints, which is 0 to a, but we're going to multiply the result by 2 because this the figure only gives a hemisphere. 2 times 2 pi the value of y, which is the square root of a squared minus x squared times ds, and that would be the square root of 1. Oops. Let me do this way. So what is ds? So what is 1 plus dy dx squared? 1 plus dy dx quantity squared is equal to 1. I can have to square this, gives me an x squared times an a squared minus x squared to the minus 1 power. So in other words, this is given by, if we like, I can rewrite this by combining fractions as a squared minus x squared plus x squared. So a squared over a squared minus x squared. I believe that's correct. So therefore, when I take the ds term is the square root of a squared over a squared minus x squared dx. Okay, so so that's what you get, and there's cancellation. It's twice the integral from 0 to a. This square root and this in the square root cancels, and you're going to get 2 pi a dx. In other words, it's 4 pi. It's 4 pi times a times x from 0 to a, and this gives me 4 pi a squared. Okay, so that's the answer for the surface area of a sphere. Okay, so let me move to the next problem. But before I actually move to the next problem, what about the rotation about the y-axis if you have a curve? Well, suppose you have a curve, maybe it looks like this, and we rotate it around the y-axis, and maybe it's x equals g of y. So and y is between c and d. So then the surface area in that case is the integral from c to d of 2 pi x ds, where ds is as before. Okay, so ds in this case would be the square root of 1 plus dx dy squared dy, and dx dy is of course g prime of y. Okay, it's also, as before, 1 plus dy dx squared times dx. Okay, so let's try an example. So let's take y equals x squared, and we rotate about the y-axis. Okay, so, and we do it for y between 1 and 4, let's say. That means x is between 1 and 2, by the way. Okay, so here's the picture. Y equals x squared is part of a parabola. Maybe it looks like this. And we're rotating it around the y-axis. So the surface area is going to be the integral of 2 pi x ds. And we're going to express this either as an integral in terms of x or an integral in terms of y. And there are several methods we can use. Method 1 we can think of this as the integral in terms of the x variable. So if it's in terms of x is going from 1 to 2, it would be 2 pi x times the square root of 1 plus dy dx squared. Now, y is x squared, so dy dx is 2x, so it would be 2x quantities squared dx. That would be one way to do it. Method 2 is to do it in terms of y. So y is going from c to d, so y is going from 1 to 4, and it would be 2 pi. Now, what is the value of x? Well, y is x squared. That's the same thing as x equals the square root of y. So we're trying to get this in terms of y. So it would be the 2 pi the square root of y times the square root of 1 plus dx dy squared. What is dx dy? Dx dy is 1/2 y to the minus a half squared, and then you're going to get a dy. Both these integrals will give the same answer, and they're both about as equally as difficult, but so I'm going to just do method 1. You're free to try method 2. You'll get the same answer with a little bit more algebra, the slightly more algebra in method 2. Okay, so let me do method 1. Okay, so what was the integral we got? The integral we got was the integral from 1 to 2 of 2 pi x times the square root of 1 plus 2x quantities squared dx, which is the same as the integral from 1 to 2 of 2 pi x square root of 1 plus 4x squared dx. This is going to be a u substitution. U will be 1 plus 4x squared du is 8x dx. We don't have an 8x dx, but we do have an x dx. So 1/8 du is x dx. And then we have to figure out the limits of integration. So when x is 1, u is 5, and when x is 2, we get 17 for u, and it'll be 2 pi x, 2 pi. We have an x dx here, but we know that's 1/8 du, and then we have the square root of u. In other words, if we bring the constants out, we have pi over 4, the integral from 5 to 17 of u to the 1/2 du, which is pi over 4 times 2/3 u to the 3/2 from 5 to 17. So this is going to give me pi over 6 times 17 to the 3/2 minus 5 to the 3/2. That's the answer. Okay, so that gives us an answer. You know what? I think I'm going to actually do method 2 just for the sake of completeness to show you that it's not much harder. It's just a little more algebra. So let me clear the screen. So recall this is the integral of from 1 to 4 of 2 pi x times the square root of 1 plus dx dy. X was the square root of y, so dx dy is 1/2 y to the minus 1/2. So we're going to get 1/2 y to the minus 1/2 squared, and then you're going to get a dy. And x here, by the way, has to be written in terms of y, so it's the square root of y. So then this integral becomes the integral from 1 to 4. I'm going to bring the y into the square root. If you do that, you're going to get the square root. So it becomes y times 1, and then y times this expression will give you a 1/4 dy. Okay, so then we'll do a u substitution. U is y plus 1/4. Du is dy to give me the integral from 1 to 4. Nope, it's not 1 to 4 anymore. It's something else. So it's 5/4 to 4 1/4, which is 17/4. U to the 1/2 du, which is 2/3 u to the 3/2 from 5/4 to 17/4. And I forgot the 2 pi. Sorry, there's a 2 pi here, there's a 2 pi here, 2 pi here. So it becomes 4 pi over 3 times 17/4 to the 3/2 minus 5/4 to the 3/2. And with a little bit of arithmetic or algebra arithmetic, pi over 6 times 17 to the 3/2 minus 5 to the 3/2. And this gives the same answer as before. So as you see, it wasn't much harder. Okay, so this is a short lecture today. I don't want to cover more than one section in a lecture typically, so this is it for today. Have a good day.